Hello and welcome back. We were studying complex Fourier series. We saw that almost any periodic signal xt can be written as a sum of complex exponential signals e to the power j omega nt, where omega is 2 pi over t and t is the time period of x. Now x is normally a real valued signal. That means at any point of time the value that x will take is a real value. However, this e to the power j n omega t, these exponentials, they are complex function of time. So we are making a real valued signal with a combination of many complex valued exponential periodic signals. Now this e to the power j omega nt, these are called the complex harmonics of xt, and these coefficients are the complex Fourier coefficients or the amount of different harmonic component present in xt. Given xt, if you want to determine the amount of different harmonic components, you can use this rule that we have derived yesterday. And we also saw that these coefficients occur in pairs of complex conjugates. They occur in complex conjugate pairs. C minus n is C plus n star. And we also saw that you can visualize these complex exponential signals as spirals in a three-dimensional plane. This is time axis, and Cn e to the power j omega nt will be a spiral rotating anti-clockwise like this, whereas Cn star e to the power minus j omega nt will be rotating clockwise. And these two signals start from opposite or symmetric positions at t equal to 0. We have seen this yesterday. And these are periodic signals, and the time period of e to the power j omega t is t equal to 2 pi over t, and the period of e to the power j omega nt is 2 pi over omega n. Now, while deriving the formula for determining this coefficient Cn, we also saw a very interesting fact, that is, if you have a complex exponential signal e to the power j n omega t, and if you multiply it with e to the power j minus k omega t, and then if you integrate it over a complete period t, that means over the time of 2 pi by omega, then this result is 0 if n and k are not equal, and if n and k are equal, then they will cancel each other. We will have integration of 1, that means it will be equal to t if n is equal to k. This was the fundamental idea that we have used to derive the expression for complex Fourier coefficients. Now we will see this rule have another very nice implication. Okay, so let us see that. We are going to derive an expression for the power of a periodic signal in terms of its complex Fourier coefficients. Imagine a periodic signal xt with time period t, for which the complex Fourier series looks like this: Cn e to the power j omega n t summed over n equal to minus infinity to plus infinity, and these coefficients Cn are known to us. Now the power, as you may recall, for a periodic signal is given as xt square integrated over a complete cycle divided by the time period. This you may also write as 1 over t integration of xt multiplied with xt dt over a complete cycle. Now normally the signals that we deal with are real valued signal. So x is a real valued signal. So if I take the complex conjugate of x, it will be x itself. So I can put a star complex conjugation here. Also please note that for complex valued signals, which we will not deal with, for them this is actually the definition of power. Okay, now let me put this expression in place of x. So it becomes Cn e to the power j omega n t summed over n equal to minus infinity to infinity. This is the first xt, and in place of the next xt, let me write c k e to the power j omega kt summed over k equal to minus infinity to plus infinity, then conjugate of that. I can use any index variable n or k because anyway it's a dummy variable, and so whether I'm using n or k, it's not a problem. Next, here, because of this conjugation, I will write it as summed over k equal to minus infinity to infinity, c k star and e j omega k t will become e to the power minus j omega k t. Now we have 1 over t integration over a cycle. Then let me expand this summation as c0 plus c1 e to the power j omega 1t, and on the other side c minus 1 e to the power minus j omega t, and this sum will continue over minus infinity to plus infinity. Next, consider the sum inside this second parenthesis. This is again very much similar to this first series of terms. Let me write here c0 star, then plus e to the power c1 star e to the power minus j omega 1t plus dot 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 up to plus infinity, and on the other side c minus 1 star e to the power this will become plus j omega t dot 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 up to minus infinity. Now we have to multiply each term in this first pair of brackets with each and all terms inside this second pair of brackets. Like this term will get multiplied with this, also with this and this, and so on. Similarly, this will get multiplied with this, 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 and so on. Now, among so many possible pairs, after integration, most of them will give us 0. That is because when we multiply two exponentials and integrate over a cycle, unless these two coefficients n and k are cancelling each other, the result is 0. So only when this n and k they cancel, those terms will survive. So if I write this summation in this way, sum over Cn e to the power j omega nt, each of these terms for each value of n will get multiplied with ck star e to the power minus j omega kt. So for all k minus infinity to plus infinity, and for all n minus infinity to plus infinity dt. So we will have so many terms, but only those terms where n and k are equal, they will survive after integration, others will be 0. So let me write only those terms where n and k are equal. So we have summation n equal to minus infinity to plus infinity Cn e to the power j omega nt, and C, in place of k I am putting n star e to the power minus j omega. In place of k I am putting again n, because only if k is equal to n those terms will survive, and I need not take another sum because only those values of k will survive which are equal to n. Now this is equal to Cn star e to the power plus j omega nt and minus j omega nt will cancel and give 1. Now we can interchange the integration and summation, the order of them. So let's put the summation first, then the integration. Now this is 1 over t summed. Now Cn star is not a function of time, so we can put it outside the integration of dt in from minus infinity to plus infinity. So this is and this integration of dt over a cycle will give t. So cancel these two t's, and finally we have sum over Cn star from n equal to minus infinity to plus infinity. This is the power, average power over a cycle of x t, and this is possible, I mean this is true, because when you multiply this series of terms with this series of terms, most of them become 0 whenever whenever the frequencies match, those terms survive. So this is a very important result. Now here is a homework for you to derive the expression of power in terms of the real Fourier coefficients a0, an, bn. We have found the power in terms of the complex Fourier coefficients Cn, and you have to do it in terms of a0, an and bn. There again similar idea will be very useful, that sine n omega t multiplied with cosine k omega t and then integrated over a complete period of 2 pi over omega. This is always equal to 0, and you know that sine n omega t, another sine k omega t integrated over a complete period gives 0 if n and k are not equal, and similarly two cosine signals n omega t and k omega t integrated over a complete cycle gives 0 if n and k are not equal. So this will be useful in deriving the expression of power in terms of A0, An and Bn. Next, we shall see a relation between the Fourier series of a signal and the Fourier series of its derivative. Okay, suppose the Fourier series of a periodic signal xt is like this: Cn e to the power j omega n t, n from minus infinity to infinity. If x is periodic, definitely then dx dt will also be periodic with same time period, and therefore you can write it as a Fourier series. Suppose it is Cn prime e to the power j omega n t, in running from minus infinity to plus infinity. Now what is the relation between Cn and Cn prime? Okay, now from here if you differentiate both the sides with respect to time, we will have dx dt is equal to sum over Cn. Cn are constants, then derivative of e to the power j omega t is e to the power j omega n t multiplied with j omega n. Now comparing this equation with this equation, you can clearly see that Cn prime is Cn multiplied with j omega n. From this you can also say that Cn is equal to Cn prime divided by j omega n, but that is true provided n is not equal to 0. Otherwise you cannot divide. And in the same way, if you consider the second derivative of x, and suppose the Fourier series of the second derivative looks like this: Cn double prime e to the power j omega n t, then in the same way you can say that Cn double prime will be equal to, from here you can say, will be equal to j omega n multiplied to Cn prime. That means it will be equal to j omega n multiplied with j omega n Cn from this equation. Okay, so in general, if you consider the third derivative, fourth derivative, fifth derivative of x, then the Fourier coefficients of that will be equal to the Fourier coefficient of x multiplied with j omega n 3 times, 4 times or 5 times. Now let us solve an example problem using this relation between the Fourier coefficients of a function and its derivatives. So here is the question. We are given a triangular waveform and we have to find the Fourier series of this triangular signal xt. The way we will do it is that we will first find the time derivative of this signal. Here the slope is 1, so time derivative will be constant 1. Then here it goes down with a slope of -1. Then again +1, and again here -1, and so on. Now this is a square wave, and we know already how to find the Fourier coefficients for such a square wave, but this time we will do it differently. We will calculate the time derivative of this signal first. So we will calculate the second derivative of x, and as you can see here the signal is constant, so the derivative will be 0. Here again constant, derivative 0, again 0 here. It is 0 almost everywhere except at this point of jumps or discontinuities. Now at this point there is a step jump, positive jump from -1 to +1. So the derivative will be a delta function like this. Call it 2 delta t. 2 because the amount of jump is 2. Then here we have a negative jump which will result in a negative delta function -2 delta t minus 2. T minus 2 because it occurs at time t equal to 2. Then again here another positive delta function. It will be 2 delta t minus 4. Here a negative one, minus 2 delta t plus 2. Now we shall first find the Fourier coefficients of this signal, second derivative. Suppose the Fourier series for the second derivative is like this: sum over Cn double prime e to the power j omega n t, n running from -infinity to +infinity. And suppose the Fourier series of this square wave, that is the first derivative, is like this: dx dt equal to sum over Cn prime e to the power j omega n t. Then this Cn prime will be given as Cn double prime divided by j omega n. This is true because of this. And then if the Fourier coefficients of xt is Cn, then Cn will be Cn prime divided by j omega n, that is equal to Cn double prime divided by j omega n whole square. So we shall first calculate Cn double prime, from that we will calculate Cn prime, and from that we will calculate Cn. So let's start with Cn double prime. Now Cn double prime can be written as 1 over time period integration of this signal d2x dt2 e to the power j minus j omega n t over a complete cycle, and I can choose any complete cycle starting from any arbitrary point. Let me say choose a cycle say from here to here, that is from here to here. Call these points as A and B. This is a complete cycle. Okay, so let me integrate it over A to B. Now within this region A to B, this signal is same as sum of two delta signals, 2 delta t minus 2 delta t minus 2 e to the power minus j omega n t dt, and this will be equal to 1 over t. You can take these two common outside, and then the result of integrating delta t multiplied with this exponential will be same as e to the power minus j omega n 0 in place of t, because this delta function occurs at t equal to 0. And in the same way, the result of this delta function multiplied with this exponential after integration will be e to the power minus j omega n 2 in place of t, because this delta function occurs at t equal to 2. Okay, now you may simplify this a bit by taking e to the power minus j omega n 1 common, like this. It becomes e to the power minus j omega n minus 1, then minus e to the power minus j omega n plus 1. Now this 2 minus goes away, so we have 2 over t e to the power minus j omega n, and this term inside the bracket is nothing but sine omega n multiplied with 2j. Now let us put the values of t and omega. So here you can see the time period is 4. T is equal to 4 and omega will be 2 pi by 4, that is pi by 2. So let us put the values. We will have 2 over 4 and then one more 2j, so let me write it 4j, then e to the power minus j pi by 2 n from here, and then sine pi by 2n. Now this part you can write as e to the power minus j pi by 2 whole to the power n. So this is becoming j e to the power minus j pi by 2 is same as 1 over j to the power n sine pi n by 2. Now this is same as j to the power 1 minus n sine n pi by 2. This is Cn double prime. Now from this, let us calculate the Fourier coefficients for dx dt. Cn prime equal to Cn double prime by j omega n. So Cn prime is Cn double prime divided by j omega n, that is equal to j to the power 1 minus n sine n pi by 2 divided by j, omega is pi by 2 n. So we will have j to the power minus n, then sine n pi by 2 divided by n pi, and these two we can put above. Now this is equal to 2 j to the power minus n divided by n pi multiplied with sine n pi by 2, and if n is an even number, okay, then this sine term will be 0. If n is even, and otherwise we will have 2j to the power minus n by n pi, and this will be sine n pi by 2. Okay, now n is odd, means n equal to 1, 3, 5, 7, etc. So let us write this is equal to 0 if n is even, and if n is like say 1, 5, 9, etc., in that case sine n pi by 2 will be plus 1. Okay, so we will have plus 1 and then 2 by n pi, and this will be 1 over j, and then if n is 3 plus 4 7, 7 plus 4 11, etc., in that case sine n pi by 2 will be minus 1, then this 2 by n pi as it is, and this j to the power minus n will be j. Now this can be written as 0 if n is even, and you can see that these two can be written together as 2 over n pi by j, n pi j, if n is odd. That is the Fourier coefficients of dx dt. This signal, this square wave. Now let us check our answer with what we got yesterday. Okay. Here, yes, here is the answer. For square wave, it is 0 if n is even, and otherwise this is 2 over j pi n, exactly what we got today. So this is C n prime, and from this we will calculate Cn, that is what we actually want, as Cn prime by j omega n. So that will be equal to 0 if n is even, and otherwise 2 by n pi j and one more j, so that will become minus 1, then omega n, and omega is pi by 2 times n if n is odd. That means this will be equal to 0 or 4 by n square pi square. So that is our answer to the question given. That means the Fourier coefficients of this signal, but that is wrong. Almost correct, but not completely correct, because this rule Cn equal to Cn prime by j omega n is only applicable if n is not equal to 0. Okay, so if n is equal to 0, we have to calculate C0 separately, not using this rule. So this is true only if n is not equal to 0. But we can calculate C0 directly in this way: xt e to the power j omega 0 t dt integrated over a complete cycle divided by the total time period, and this is equal to 1 over t integration xt e to the power 0 is 1 over a complete cycle. So this is nothing but the average value of xt, and the average value you can calculate as 1 over total time into area under xt within one cycle. Now let us look at the signal. Okay, from here time period is 4 and the area under one cycle is half into base 4 into height 2. So this will be 1 over t into area is half into base time period into amplitude, which is 2, and this becomes 1. So that is the value of C0, and for other n, these are the values of Cn's. You should also understand this fact that it is not possible to calculate C0 as C0 prime by j omega n, because when you differentiate a signal, then the average value will have no effect. You can add any constant to a signal, but the derivative will remain same. So the average value, which is a constant, will have no effect in the derivative of the signal. And then when we are calculating Cn prime, that is the Fourier coefficients of the derivative, that will not depend on the average value of the original signal. So the information about the average value of the original signal will be completely lost in Cn prime. So you cannot calculate average value or C0 from C0 prime in any way. Let us now talk about spectrums, magnitude and phase spectrum. For that, consider the square wave we discussed yesterday. This is the square wave for which we calculated the complex Fourier coefficients as equal to 2 over j pi n for n being odd and equal to 0 when n is even. Now, so we can write C0 is equal to 0, then C1 is equal to 2 by j pi 1, 2 by j pi 1, C2 will be 0, C3 will be 2 by j pi 3, C4 will be 0, all even coefficients are 0, and C5 is 2 by j 5 pi. On the other side, we have C minus 1, minus 2, minus 3, C minus 4 and C minus 5, so on. Okay, dot 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 dot. Then C minus 2 will be 0, C minus 4 will be 0, even coefficients are 0. Then C minus 1 is 2 by j minus pi, like this. C minus 3 is 2 by j minus 3 pi, like this, and C minus 5 is 2 by j 5 pi minus. Now these are complex numbers in general, so we can write these numbers in terms of their magnitudes and angles. For example, C1, it has a magnitude of 2 by pi with angle 1 over j, that means minus 90 degree. Then C3 is equal to 2 by 3 pi with angle minus 90 degree again, and C5 is equal to 2 by 5 pi with angle minus 90 degree. C minus 1, that is equal to 2 by pi with angle so minus 1 by j, that is plus 90 degree. C minus 3 has a magnitude of 2 by 3 pi with angle minus plus 90 degree. C minus 5 is 2 by 5 pi with angle plus 90 degree. And these coefficients, even coefficients, are 0. Now this long list or table can be represented nicely in the form of a graph. Along the horizontal axis, we will plot different omega values like 0, then 1 omega, 2 omega, minus 1 omega, minus 2 omega, etc. in this way. 1 omega, 2 omega, 3 omega, 4 omega, 5 omega, and so on. On the other side, minus omega, minus 2 omega, minus 3 omega, minus 4 omega, minus 5 omega, and so on. So, and along the vertical axis, we will plot the magnitude of Cn for different n values. So here n is equal to 0, 1, 2, 3, 4, 5, minus 1, 2, 3, 4, and minus 5. These are different n values, and these are corresponding omega values or frequencies. Now C0 is 0, so we will plot 0 here. Then also C2, C4, C minus 2, minus 4, they are all 0. So at 2, n equal to 2, 4, minus 2, minus 4, we will plot 0. Then C1 has a magnitude of 2 by pi. So here we will draw a bar or a line with height equal to 2 by pi. Okay, then C minus 1 also has a magnitude of 2 by pi. So here also at minus 1, n equal to minus 1, or at minus omega, we will draw a bar or a line with height 2 by pi. In the same way, C3 has magnitude 2 by 3 pi. So here we will draw a shorter bar, shorter line with height 2 by 3 pi. And C minus 3 also has same magnitude. So here also another bar with same height 2 by 3 pi. Similarly, at n equal to 5, C5 has magnitude of 2 by 5 pi. So even shorter bar with height 2 by 5 pi, and here as well at minus 5, 2 by 5 pi. Okay, in the same way we will draw another graph with x-axis as the frequency. Okay, and we will mark n equal to 0, 1, 2, 3, 4, 5, minus 1, 2, 3, 4, 5. These are the values of n, and correspondingly the frequencies are 0, omega, 2 omega, 3 omega, 4 omega, and 5 omega. Here as well, minus omega, minus 2, minus 3 omega, minus 4 omega, minus 5 omega. Then along the vertical axis, we will plot the angle of this CNs. Okay, C angle of CN. Now you see that the angle of C1 is minus 90 degree. C3 also has same angle minus 90, C5 also has same angle minus 90 degree. So I will draw bars here, minus 90, minus 90, and minus 90 degree. Okay, all with same heights. And C minus 1, minus 3, minus 5, they all have angles plus 90 degree. So I will draw bars here in the opposite direction. with amplitude proportional to plus 90 degree, like this. And then these even coefficients which are 0, for them we can use the phase angle as 0. By phase angle I mean the angle of Cn. Now this graph is called magnitude spectrum, and this graph is called the phase spectrum. By phase we mean the angle of Cn. Okay? Now one thing we know that these coefficients, they occur with complex conjugate pairs like this. C minus 4 is complex conjugate of C plus 4 and so on. Therefore, the magnitude of say C minus K will be same as the magnitude of C plus K. Like magnitude of C minus 3 is same as magnitude of C plus 3. Therefore, this magnitude spectrum will be symmetric, or you can call this as an even function of n or omega. However, since these are complex conjugate pairs, this is true for real valued signals. Therefore, the angle of C minus will be negative of angle of C plus 1 and so on. Therefore, this phase spectrum will be antisymmetric, or you can call this an odd function of n or omega. Now, these two graphs together is called spectrum of the signal. They together gives us an idea about what are the different frequency components present in a signal and what are their relative amounts, etc. We write any periodic signal, almost any periodic signal, as a sum of complex exponential signals e to the power j omega n t, n running from minus infinity to plus infinity. This is called complex Fourier series. These coefficients are called complex Fourier coefficients. These exponential signals are the building block or ingredients that make up this periodic signal xt. These are called the harmonics or complex harmonics. The exponent here is called frequency. These coefficients Cn can be written as the magnitude with the angle of Cn. These are all complex numbers. This is called the magnitude, and this is called phase. So this graph, where we have magnitude of different coefficients as a function of frequency or n, is called magnitude spectrum, and this graph where we have phase angle, that is the angle of different coefficients as a function of n or omega, is called phase spectrum. Now you can plot magnitude and phase spectrum for any periodic signal, and I will leave it as a homework for you to plot the magnitude and phase spectrum for this triangular wave. Please remember that for real valued signals, magnitude spectrum is always symmetric and phase spectrum is always antisymmetric or odd in nature. We shall finish today's class after solving one or two example problems. Okay, so here is the first question. Prove that if xt is a even signal, that means x minus t is equal to xt, then c minus k will be equal to ck. So that means these coefficients will also be an even function of the index k. To prove that, let us first write ck equal to 1 over t integration e to the power xt e to the power minus j omega k t dt over a complete cycle. Any complete cycle, maybe we can take 0 to t. Now c minus k will be same thing with minus here. Now this we will put t equal to minus tau or tau equal to minus t. So apply this change of variable so that d tau will be equal to minus dt, and therefore c minus k will be equal to 1 over t integration. The limit will change, will become tau equal to 0 to minus t. X in place of t put minus tau, and e to the power minus j omega minus k, then put minus tau. In place of dt put minus d tau. Now then 1 over t. Here we have a minus sign. Using this minus sign we can change the limits. We can make it from minus t to 0, and we will make this as plus d tau. Here x minus tau is same as x plus tau because x is an even function. Then e to the power minus j omega minus k minus tau will become plus k tau. Okay, or let me write it nicely. Now you see that this is nothing but ck, because we have, or you can write one more step. This is 1 over t. Integration is actually over a complete cycle. Now tau is a dummy variable, so you may put in place of tau any other variable you like. I am putting t, and this now clearly looks like ck. So that is the proof. Now an important observation you can make from this result, that if xt is real valued then we know that C minus K is equal to C plus K star complex conjugate. And if xt is also even, then we got C minus K equal to Ck. So this implies if xt is a real valued function and also even function, then we will have Ck and Ck star being equal. So Ck will be equal to Ck star. That is only possible if Ck is a real number. That means if we have a even real valued function, then the Fourier coefficients, complex Fourier coefficients will all be real numbers. Next, I shall leave it as a homework for you to prove that if xt is an odd signal, that is x minus t is equal to minus xt, then C minus K will be equal to minus Ck. Okay, I shall leave it as a homework, and from this you should also show that if xt is a real valued odd signal, then Ck will be purely imaginary. This is your homework, and we already have proved that if x is real and even, then Ck is purely real number. Thank you. See you in the next class.